Hello, and thanks for your interest in our work. My name is Hongyao. I'm on the faculty of Columbia Business School. Today, I'm going to talk about the matching between jobs and workers in two-sided platforms. The goal is to use data to improve the efficiency and reliability of the matching algorithms for these scenarios where it is inevitable that some jobs are more lucrative than the others. To start with some examples, think about Uber and Lyft's matching riders and drivers, and also consider Instacart and Amazon's assigning grocery delivery jobs to their workers. Things can very easily go wrong if a platform naively adopts an algorithm that seems to be optimal. So here's a Bloomberg article talking about how Amazon drivers are hanging their phones in trees in front of a Whole Foods market. The drivers are doing this because they figured out that the algorithm always assigns new jobs to a closest driver, so everyone wants to get closer and be the first in line to get the next job offer. For Uber and Lyft, they will be in so much bigger trouble at the airport if there are 200 drivers all trying to get very close to the terminals. So instead of assigning to a closest driver, the ride-sharing platforms maintain some virtual FIFO queues for drivers who are waited in a designated waiting area. And for a driver in this waiting lot, they can get in the virtual queue, and here is a screenshot showing that the driver is in the queue and the driver is at the 161st position. So this solves the congestion problem, but as we'll see, simply moving to FIFO dispatching has its own unintended consequences. The first challenge is that the earnings from a trip varies a lot by destination. This is a heat map showing the average fare by destination for trips originating from Chicago O'Hare, which is roughly here. We can see that a short trip to a close-by area pays on average $10 to $20, but a longer trip can pay as high as $60. So naturally, the drivers will have an incentive to cherry pick. And FIFO dispatching substantially exacerbate the problems of cherry picking, especially for markets where the drivers can already see where the trip is going before they need to decide whether or not to accept. The reason is that in a major US airport during the busy hours, for a driver at the head of the FIFO queue, the driver will be getting one new offer on average every 5 seconds. So the cost of cherry picking is very low, and it's not surprising if the driver just sits there for half an hour, declines every single dispatch until the driver receives the trip that's paying $100. And the exact same reasoning can be repeated for the second and third and fourth drivers in the queue. And this brings us to the second challenge, which is that the riders have very limited patience. If I were a rider requesting a trip to a low earning area, my trip is offered to the first driver, second driver, and third drivers in the queue, but none of them is willing to take me. And by the time my trip is rejected by the 12th driver, I've been waiting on the screen for 2 minutes, and not knowing what's going on, it's very likely that I'll just cancel the request. So this leads to not only poor reliability for the riders, and also low trip throughput and low revenue for the platform. So what can be done here? The ideal solution is to use pricing. So we should price the trips by destination such that the drivers are making the same amount of money from all of the trips. But this is very difficult to implement in practice. First, reducing the earnings for long trips is difficult because the platform promises certain per mile and per minute rates for the drivers, and it's very difficult to go below those. On the other hand, we show that it is also suboptimal to triple the fares of these short trips in order to match the earnings from these long trips, because we'll lose the rider demand, and overall that would lead to an even worse outcome. So in this work, we propose mechanisms that align incentives using both time and money. We first introduce the direct FIFO mechanism, and this, for the lower earning trip, instead of sending the trip to the head of the FIFO queue, the direct FIFO mechanism will send these trips further down the queue where the option to skip the rest of the waiting will incentivize the driver to accept the dispatch. And we show that in equilibrium, the mechanism will achieve the optimal welfare and throughput that's achievable when the drivers are strategic. And in practice, it is still nice to maintain the property where the drivers who had waited the longest times in the queue will have higher priority for all of the trip, regardless of the destination. And we can imagine this will be considered more fair by the drivers, and it will also be more robust to the driver's idiosyncratic preferences. So to achieve this, we propose the randomized FIFO mechanism. Instead of sending a trip directly to certain positions in the queue, the randomized FIFO mechanism will gradually send each trip down the queue in a randomized manner. And this randomization will increase the amount of time a driver will have to wait for the next dispatch if the driver declines the current one. And this increase in the cost of cherry picking helps us with aligning incentives. For more details on these mechanisms, please take a look at our poster. And we also include some counterfactual simulations using ride-sharing data from the city of Chicago. What these results show is that the proposed mechanism will achieve substantially higher revenue and throughput in comparison to the status quo strict FIFO dispatching. The results also show that overall, the variance in the total payoffs of the drivers is very small. So the outcome under these mechanisms are effectively envy-free. And this is also a very important consideration in practice. Please feel free to get in touch if you have any questions. Thanks a lot.